Hi, this lesson is going to be a follow-up to the Flint water crisis. This is a skew the script lesson, but this is going to be using some sample data that we're going to collect. In your notes, this is going to be from pages 20 to 22. This is Unit 6, Lesson 6. And it's going over a one sample z-test for P. So let's recall the previous lesson. We had some original sample data where we sampled 252 homes, and 42 of those homes had high lead level content. And what we're trying to test is there enough evidence to conclude that the percentage of homes have higher than or 10 more than 10% of the homes have a high lead content? And so our null hypothesis was no, the houses have 10%, 10% of the houses have a high level content. And the alternative would be no, we're trying to prove that there's more than 10% of the households that have high lead level content. So it's always going to be equal for the null and always going to be in whatever the direction you're trying to prove. So in this case, it's greater than. So let's just recall how to use the calculator to get a z and a p-value. You're going to press stat. You're going to go over to tests, and you're going to go down to 5. This is a one proportion z-test, one sample z-test for p, and your calculator calls it a one prop z-test. In here, PO, that's your null hypothesis percentage, or as a decimal, so we're going to do 0.1. Your X, well, that's going to be 42 total number of successes. So there were 42 houses, I shouldn't say successes in this case, but there were 42 houses that had high lead level content out of the 252 for your N. We want to make sure we use the greater than since our alternative is greater than. Now you have two options when it comes to your one prop z-test. You can calculate or draw. I like the draw function. It shows you what that graph looks like, and it'll give you two things that are important. It's going to give you a z, which you must write down when you're doing your do part, and that's about 3.5 standard deviations above the mean. This is a normal curve centered at 0, and the standard deviation is 1. So it is standardized already. So z-scores are what it's reading. And you're going to notice that the probability, the p-value, the probability of the z being at this value or more extreme is very low. In fact, that's 0.0002. You can also run the test by doing calculate, and it'll give you the sample proportion as well, which is about 16.7% in the N value. So it does give you a little bit more information, but it doesn't give you the picture. And so as you recall, with a p-value so low, we're going to reject this. We say we have enough evidence to conclude that the percentage of homes in Flint that have a high lead level content is higher than 10%. Okay, so we have statistically significant evidence. Now, what we're going to do with our sample is we're going to randomly pick some numbers from the household data. So in class, I had you pick 5 samples apiece, and we combined our data, and we might have had 80 or 70, depending on how many people were in class. But let's say I only did 5 numbers, right? And if I did a random sample of 5, so if I go to like math and go to prob ran int, let's say I just make my lower one. I have 1,000 households on this page. So I'm going to go to 1,000. And I could click 5 and just have all 5 go. I'm just going to do one at a time. And I'll press enter. 944, 909, 147, 515, and 406. So I'm going to quickly look at and circle those. 944, 909. Let me get those here. I have them circled on here, and you're going to see that on our handout, what's going to count as a high lead level content is anything above 15 parts per billion. And we're really trying to figure out how many of our sample are high lead level content. So that's not high. 0.0 is not high. Another 0.0. 21, that's going to be considered high. And 15.4 is also above 15. So in my case, I have 2. Now, if that's all my sample had, we would violate the large counts condition because the NP and the N1 minus P would definitely be less than 10. But let's just assume that we're ignoring conditions for a moment. And if I were just going to use, 2 out of 5 as my proportion, well, 2 out of 5, that's 40%, guys. And of course, yeah, that's a pretty high percentage compared to our null, which is 10%. But with only 5 in our sample, does that really provide statistically significant evidence to favor the alternative hypotheses? And the jury's kind of out on that because we haven't run the test yet, but we can run the test with 2 out of 5 and see what's happening. So if I go to stat and I go to test, one prop Z test, and I put 2 out of 5 and kept everything the same, and you're going to see, even though our sample proportion was significantly higher at 40%, you're going to see that p-value being much bigger than that 0.0002. And that has everything to do with the sample size. We had such a small sample that the likelihood of getting 2 out of 5 isn't that isn't terribly low. It's pretty low here, right? I mean, it's still less than 5%. So I do have enough evidence to reject the null hypothesis if alpha is at 5%. But it's not as strong as the 42 out of 252. And I could do this again, but ultimately what I want to do is take a large enough sample where we can have statistically significant evidence. So I'm going to do that real quick, and then I'll report my numbers. Okay, guys, I went back and I did another random sample, and I took 100 in my sample size, and I found that out of the 100, so we're going to say n equals 100, I got 15 of those homes to have high lead level content. Okay, so 15 out of my 100. And the number of low lead homes in this case would be 85. So I'm going to use that to run my test, and we're going to check the p-value and the z first, and then I'll show you how to write it up in the 4-step plan. So we'll go back into the stat menu, and this time we're going to go to one prop z test. Still 0.1. We're still going to put our success, our number in our sample that had high lead homes, and we'll do 100 there. Keep that greater than. And I'm going to go to draw so I can visualize what's going on with this. And it looks like my z-score, the number of standard deviations above the null, is about 1.67. And the p-value, the probability of getting a z-score that value or more extreme in this direction, is just under 5%. So out of my smaller sample, 100, I still have pretty significant amount, significant evidence that the alternative is true because that's under 5%, but it's nowhere near the 0.002 or 0.0002 that the 42 out of 252 represented. So let's write that up. When we're going through the state plan do conclude process, we always want to make sure we set up hypotheses first and name the test. You can name the test under plan. I like to name it under state. So this is just a one sample Z test for P. Your calculator says one prop Z test, but you'll write one sample Z test for P. You'll do your ho and your ha. And it's just P equals 0.10. P is greater than 0.10. Okay, the ha depends on the direction you're going, but unsafe means is more lead content in this case. We define our P. We define what the parameter is. So our P stands for the true proportion of homes in Flint with high lead. And we also want to set our alpha level. What is our alpha level? Well, if it doesn't say, I usually default it to the 5%. So we just simply state alpha equals 0.05. We want to compare our p-value to this number here. Now our plan part is talking about conditions. And if you haven't already written your p-hat, you can do that here real quickly. My p-hat was going to be 15 out of 100, which is about 0.15. So we have some evidence to conclude that the alternative is true because this is greater than the 0.1. So I have numbers greater than that 0.1. So I'm going to conduct this test. If my sample was 8 out of 100, then it would make no sense to do this test because I don't even have a sample proportion larger than your null hypothesis proportion. So that wouldn't be an appropriate time to use the test. The plan part is your random, independent, and normal. So your random, your 10%, that's your independent, and your normal, which is your large counts. What you do on these three conditions is you simply kind of reiterate what we did here. A random just indicates that we took a random sample. It's usually implied that we do, but we want to write that. So we said a random sample of 100 homes was taken. Now we're going to go to our 10% condition. Now the paper that I did my random sampling from had 1,000 homes on it, but that's not all the homes that were in Flint. We know that 100 is less than 10 is 10% of 1,000, but it's definitely less than 10% of all homes in Flint. So we can simply say 100 is less than 10% of all homes in Flint. We don't need to necessarily do the 10% condition if it's an experiment and you're just separating volunteers out. But if you're sampling from a larger population, you want to make sure you're using that rule because the value of the probability of selecting without replacement could change if your selection is larger than 10% from your population. In your normal large counts, this does differ a little bit because what we're doing is we're not doing NP hat, okay? We don't want to do p hat because the assumption is that it's 10%, not greater than 10%, not our statistic. So we're actually going to use NP, which is your null, and N1 minus P. And both of those should be greater than 10, okay? So our P is 0.1. Our sample size here is 100. That's your N value. So it's going to be 100 times 0.1, and that is equal to 10. And then we also have 100 times 0.1 from 1, so it's going to be 0.9. And both of those are greater than 10. That allows us to use a normal curve when we're constructing our sampling distribution around it. So now we're good to go. We can actually do all the work here. Under the do part, what's important is that you have identified the test, draw a sketch, and write your test statistic. Now your test statistic is just a z-score. And it's always going to be your statistic. In this case here, it's going to be your sample statistic, so p hat, minus your null proportion. So that's just going to be p, not p-value, just p. And that's going to be divided by the standard error of your statistic. Now in your formula sheet, the standard error actually uses the p hat. But remember, the assumption is that it's 10%, not 15%. So we're actually going to use p. So we want this p to line up with that p there when we're doing our calculations. We still use our sample size, so that's still going to be over 100 in this case, but these have to be the same, okay? Now, when you're calculating that, I'm going to plug in my numbers here, and that's going to be 0.15 minus 0.10 divided by the square root of 0.10, 1 minus 0.10 over 100. And I'm going to put that all in the calculator at once. This is how I'll do it. Go ahead and jot that down and pause it if you need to. I'll do the calculations over here. I'm going to do parentheses 0.15 minus 0.1 divided by the square root. 0.1 times 0.9 divided by 100. That can all be entered in like this. And that's your z-score. So what that tells us is our z-score, the probability of getting, or the sample size, the sample of 15%, jumbled words here, is about 1.67 standard deviations above the mean if the mean were at 10%. So if we're centered around 10%. And so what that looks like on a normal curve is you're going to put your z-score here. And you can get this sketch from your draw part on your calculator. This is going to be a 0. If it's counting standard deviations, just do a rough count on there. And we want to go 1.67 standard deviations above the mean. So maybe about 1 2/3. And what we're trying to find is the probability that z is greater than 1.67. That's going to be what your p-value is in this case because our alternative is greater than. So we want to match that up with this. So if I'm going to go through and calculate that, I could go to my table A or normal CDF. I'm going to choose normal CDF. And my lower in this case, since I want to go above, is going to be that 1.67. My upper is going to be infinity, so a very large number. Leave that at 0 and 1. And that right there is the probability of getting a value, a sample that extreme or more in this direction. And you notice it's going to be about 0.0474. That's your p-value, okay? So you would say your p-value, or you could just say p, make it look kind of like that, or if you want to maybe make it distinct from the null hypothesis proportion, because people can get those confused. You write p-value, and you get about 0.047. I'll just go that far out. And that's what you want to conclude on that. So the two important things you need on here, this work, honestly, the sketch and the work, you may or may not, get docked a lot of points, for having the sketch of work. But what you always need are Z. So Z is going to be 1.67, and you need your p-value of 0.047. If you include nothing else, draw a sketch, shade, and write those two things on here, okay? Now your conclusion always is going to be linked back to your alpha level. So you would say, since our p-value uh, 0.047 is less than alpha at 0.05, we're going to reject the null hypothesis. Once we reject the null, we can say we have convincing evidence to conclude the alternative is true. So we say we have convincing evidence or you could say statistically significant evidence, convincing evidence that, well, what is the alternative? That the level of the percent of homes in Flint that have high lead level content is greater than 10%. So we say we have convincing evidence that the percent of homes with high lead is greater than 10%. That's how you do a state plan do conclude. When you do this problem or a problem like this, you don't have to write the words state plan do conclude. And as far as the do part goes, you don't necessarily need to have the work for the z-score, okay? But you do have to report that, and you have to name the test that you're going to be using. So using that technology, if you're going to rely on your technology to get this answer, my suggestion is to do the one prop z test, put this data in, and go to the draw. That way you can sketch this, you can shade above the 1.67 and report these two values, right? As long as you have your p hat somewhere in the problem, if you need your p hat to be calculated, either calculate it, here if you haven't written it here, or go back and redo it as the calculate part, and you'll have it right there. Okay. That will get you full credit on a free response. Make sure you use context and make sure you always use the null proportion because we're assuming that the null is true in this case. Okay. Now, going back to this question here, using the 42 out of the 252, says compared to our class data, does this study give more or less convincing evidence of an unsafe water supply in Flint? And why? Well, our p-value here was, while it was under 5%, it wasn't that much under 5%. So I would say our information, the data that I used for this video, gives, I would say, less convincing evidence. Since the p-value is greater. And if you remember the other one, the previous p-value was 0.0002. So while we do have convincing evidence, it's not as strong as the one with 42 out of 252. So the takeaway is take larger samples so that way you have more convincing evidence. The next page is going to be the check your understanding. I would advise that you follow that using the template. And just for a reminder here, you should have access to this template that you see here. This is on a pink handout if you're in my class. So I would look at this template, use it to help you answer the check your understanding that is on the following page on page 22. So we're going to read through this problem. Pause the video so you can read through it. I'll write out the work and I'll go through my work step by step. All right, guys, here we go. Let's go through this. So let's read through the problem. I've annotated a few things on here. Sometimes parents and grandparents like to recount how difficult life was when they were kids, such as having to walk 10 plus miles to school in the snow uphill both ways. A random sample of 180, there's your N, teenagers were selected, and 40% had heard these stories from their parents or grandparents about how difficult life was when they were kids. Well, that's your p-hat. That's your sample proportion. The question, do these data provide convincing evidence? That lets you know we're doing a test. So anytime you see that word test, at the alpha level equals 0.05, significance level, that the proportion of all teenagers who have heard stories from their parents or grandparents about how difficult life was when they were kids differs from 0.50. Now, when you see the word differs, that's going to be not equal in your alternative or is different from, okay? 0.50 is the null. That's what we're trying to compare it to. So when we set up our hypotheses, this is a one sample z-test for p, like we've been doing. Here's how you set that up. You're still going to have your ho, your ha, your p, 0.5, 0.5, but this is a not equal, and we still write our alpha. And it's good practice to report our p-hat and always state what your context is. So p is the true proportion of teenagers who have heard these stories from their grandparents. We're going to do our conditions. So we're going to do random. We have a random sample of 180 teenagers. We must write confirmation of this randomness, even though it's already stated. We also have to imply, because we're sampling without replacement, that less than 10% of all teenagers were selected, which it was, because we can assume 180 is. So we write that. And we do our large counts. And remember, we use our null, not your statistic. So we're not going to use this in there because we assume the null is true. They're both going to be, in this case here, 90, which is much greater than 10. So we can use a normal curve to model this distribution. So now we're ready to do the work. We're going to calculate our z-score. So p-hat minus p over the standard error, but this time we're going to use p because we assume the null is true and our sample size. And we get about negative 2.683. Let's confirm that in our calculator. And there's your z-score. Now in this problem, what we want to do is we want to calculate the probability of getting a value as extreme or more in that direction. But since it also said not equal, we have to flip it to the opposite side of the normal curve and do the positive as well, because differ just means it could be as far away on this side or as far away on this side. So what I would do is I would go to normal CDF and make my lower negative infinity and make my upper my z-score that I calculated. And that's going to be 0 and 1 for your mean and standard deviation since we've standardized it. And we're going to go to paste. And we get about 0.0036. Well, on the other side of that equation, or graph, if I use positive 2.683 to infinity, I'm still going to get 0.0036. So you could just simply double that. Anytime it's a two-sided test, you're going to double to get your p-value, okay? So the probability of getting a value as extreme in this direction or as extreme in this direction is the combination of those two. Now, if you don't want to do all that work, and you don't need to include this, by the way, to confirm all that in our calculator, we would just go stat tests, one prop z-test. And in this case, it's going to be the null is going to be 50%, so 0.5. Our sample was 40%. Now we don't know the counts, but if you do 0.4 times your sample size, which was 180, it'll magically calculate that. And then you can round it to the nearest whole number if it doesn't give you a whole number. And so we'll put 180 over there. We're going to select not equal. And I'm going to go ahead and click draw. And so you can see how on that picture here, it's going to give you just a slight shadedness over here and there. And that p-value, my friends, right there is the combination of this plus that. So that's your 0.0073. My calculations were 0.0072. So I mean, for all practical purposes, those are identical, okay? So our p-value in this case is very low. So since our p-value is very much smaller than 5%, we're going to reject the null. We have convincing evidence that the proportion of teenagers who've heard these stories is not 5% or 50%. Then the last question says, a 95% confidence interval for the proportion of all teenagers who have heard stories from their parents or grandparents about how difficult life was when they were kids is from here to here. Now I'm going to pull this up here because I can actually, if you've run the test, it'll pop those numbers up in your one prop Z interval. And you can verify what that interval is and see how it actually matches here. And so the question is, explain how the confidence interval is consistent with, but gives more information than the test. Well, it's consistent because what's not in the confidence interval is 0.5. You know, that's going to be over here, right? So 0.5 doesn't fall between 0.328 and 0.472. So my interval at least tells me that I have convincing evidence that the true proportion is different than 0.5. But what the interval also provides to me is the plausible range of values. So I can kind of have a little bit of wiggle room in terms of what should it be other than just straight 40%. And I could see, well, it's anywhere between about 33% and maybe 47%. That's my margin of error giving me that. So it does give you a little bit more information than the test does. Well, that's all I have for this lesson. Thanks for watching. Our next lesson will be over 2 sample z-test per p.